So back again to working group number 4, mathematics in games. So the idea of this presentation is to first of all to give you the most important things you should know about mathematics and games. This is mainly for people who have no idea how mathematics and games are connected to each other. So it is a very broad approach. So please, mathematicians from the audience, don't be mad at me. I won't be very specific, but if you want to add stuff, please do. Okay, this is the idea is really to understand what we would like to do and how games and mathematics are connected. So game theory, it exists. I mean, you can combine game and theory together. Is a real theoretical discipline, and the main idea behind that is to try to understand in a formal way the situations in which players interact. So in these situations, games are kind of a huge universe where players are decision makers.
Hold on.
And so the idea is to understand how they interact each other and how they are making decisions. So in mathematics, usually we use models. Okay, so game theory consists also of a collection of models, and these models, they are abstractions of reality, and they are used to understand what is observed or what is experienced. Thank you. So of course, we want to use these models to understand the evolution of a game, so how it will end, for example, or to advise the players on the best move to make. So very generally speaking, game theory can be used in many different other disciplines, in economics, for example, or in politics, or also in biology, to understand how, for example, a population of frogs, let's say, just evolved or developed. I don't know what. But so the question raised, the very general questions are the following. So can we predict each player's choice in this universe inside the game? What will be the outcome of these actions? So we can think of what will be the issue of the game. And for example, does it make any difference if the game is played several times? Will the outcome be the same or not? So this is very broad, as I said, game theory. Of course, the mathematics involved behind that will be different if we consider different games. And as Walter already showed us, we have really a lot of different types of games. And so it depends on the characteristics of the games. So I will give you a few examples. It won't be like an exhaustive list. I just want to, highlight the differences. So for example, a characteristic of a game could be if the game is cooperative or non-cooperative. I think I don't have to explain that. I'm sure you get what I mean. Another difference would be, is the game simultaneous? So paper, scissors, hand, or is it sequential? I mean, do we have to, each player take a turn and it's sequential? If the game is a zero-sum game or a non-zero-sum game. So basically, if a game is a zero-sum game, you have a winner and you have a loser. If someone wins, the other lose. And non-zero, you could think of gaining money, for example. So you don't have the most amount of money, but still you have some. So you're not totally a loser, but you're not really the winner as well. Let's think of that. Then you have a very important difference is the fact about the information of the game. Is it perfect information or imperfect information? The perfect information of a game is that you have all the things that you need on the table. For example, if you look at this picture, I mean, all the players at one moment of the game, they all have the same amount of information. Okay, so it's perfect information. While when you have imperfect information, for example, you have hidden cards and only you know what's on these cards, okay? And there are others, characteristics which are more complicated to explain, but you got my point. So let's just take examples of these characteristics, okay? And try to define like a specific category of games. And I will take these characteristics, so non-cooperative. I will add the fact that there are only 2 players in the game, that it will be a sequential game, zero-sum game, that we have perfect information, so no hidden cards. And I will add 2 more characteristics. For example, no chance, so no dice rolling or no shuffling cards or this kind of things. And let's think that the last move determines if there is, well, who is the winner and who is the loser, okay? Well, if you combine all of these characteristics to define a game, then we are in this category of game which are called combinatorial games, okay? I said a bit about it this morning. And these are the games I worked on, so I know them pretty well. And so, okay, you think that it's really restrictive, like you have many restrictive characteristics on these games, and that perhaps there are not so many games who have this characteristic, which is not true. We know a lot of games which have this characteristic. So the well-known examples are this one. So chess, draw, the famous tic-tac-toe that Walter loves so much. Puissance 4, Puissance 4, power 4, I don't know how you use it, okay. So these are the well-known examples. So of course you don't necessarily have a winner at the end. It can be a draw as well. And less well-known example, so we can think of paper and pencil games, such as Sprout. So it's written inside, but it's hidden right now. The dots and boxes game. We can think of games who can be played with matches or pebbles, whatever, the Nim game. And another example is the board game, whose name is the French military game. So these are examples of combinatorial games because they have these characteristics that I showed just before. So the challenge is, and this is the part where mathematician in combinatorial game theory can add things, so please do if I forgot stuff. But the idea of combinatorial game theory is to first to show the existence of a winning strategy, which is not so difficult. But then the worst part is to find it and to make it explicit. Ah, that's what you told me, admit. Sorry. Okay. Okay. Then the idea is given any position in a game, in a combinatorial game, is to try to predict the nature of this position. Is it a position who is a winning position for one player, a losing position for another player, or is it a draw? And we assume, so again, it's a model, so it's just like let's pretend both player plays optimally, which we know it's not necessarily true in real life, because sometimes people make mistakes, humans make mistakes. And to give you or to show you some example is that we are using different representations. So this is a very basic example of tic-tac-toe, and let's just pretend we would like to know, okay, what is the best move for the red? Well, obviously there's no perfect move, but it's just to highlight my points. And it's to have a look at all the positions that could follow this one. So what are the different possibilities for the red, then what are the possibilities for the blue, and then what are the different issues of that game. This is a stupid example. It's just to show you how it could be done like exhaustively. And this is just a short example on the tic-tac-toe. Just imagine that in chess. Okay, so we would need like a really huge blackboard or whiteboard, whatever. But we can use also other mathematical tools, graph theory, or also a game tree. So for example, this is the game tree for the game named Horseshoe. And you have, just in one look, you have all the different positions that can arise in the game. And in blue, these two are the winning position for blue, and in red, the winning position for red. And you have the connection, you see, with of every position. So this is also something to help us to visualize the thing. another one, which is also a way to explain my first slide, is an analysis of the domineering game. So one play, it plays with domino, these wooden pieces, and you can, well, one player can put it horizontally, and the other player can only put it vertically. And so Louise and Richard, for example, if they are playing that game, and we just analyze small individual and independent parts of the board and trying to say, okay, is it this position? Is it a position which is better for Louise or better for Richard? And depending on the issue of this situation, this particular situation, then we have more information about the board in general. Okay, just imagine that the main question is, okay, in that position, after a few turns, who has a winning position? Who is in the better position to win at the end? Is it possible to say? And which move should he do, or should she do? Those. Anyway, and one of the current challenges is, of course, not of course, but more complicated game and the score-based game. So it's to understand them theoretically and to understand, well, the position and the outcome. So score-based games such as Go, where you have to count at the end the points, Othello, or dots and boxes that I already showed you before. And this is more complex challenges in combinatorial game theory. So this was a short presentation of one special relations between combinatorial game and mathematics. Now, what are the interests for GameTable? I already, well, beyond the title of the working group, of course. Well, I already showed you this morning, but let's try to have it nicely said with slides. Is in this working group number 4, we would like to share the mathematical methodologies, and this is really broad, okay, many mathematics involved inside, and to first of all connect and highlight researchers doing work on games and mathematics. And this working group is not isolated. This is the idea of this action as well, is to have really strong connection with the other working group. So I just give like one example, but of course it has to be precise. With working group number 1, it's for example, compare the AI and the human strategy, or the human mathematical strategy. It's something that we already tried to do with Eric on a mathematical example and historical example. Connection with the working group number 3, when one of the aim is to identify mathematical principle. Yeah, I think it can be. Yeah, thank you. Of course, with working group number 5, especially on the educational potential of game in mathematics education. It's something that I said few words this morning about. And last but not least, the historical perspective. So this is highlighted because, as I said this morning, I think there is also a strong place for history in this working group and in general, and it's not just because it's my background. I think the study of historical perspective, it really allows us to deepen our knowledge in mathematics, so the connection between games, culture, and mathematics through history. And this is something which is essential for current teaching. Knowing the process of production of knowledge in mathematics, in games, is something which is really interesting for teaching. So I just give you a short but quite relevant example. The French military game. So it's a game that I showed the board earlier. So this is an asymmetrical blockade game, because as you can see, white has 3 pawns while the black one only 1. So the aim of the 2 players is not the same. And this board game, I won't give you all details about the history, but was analyzed by a French mathematician for the first time, Edouard Lucas, exactly in 1887. Well, at least it's the date of the first paper written on that. And he gave these things. So can be seen like a game tree, like the first game tree, the first analysis of this game. We are in 1887. There's no AI, so no possibility to check if this is true or it's not true. And so it was interesting, for example, it's something that we did with Walter and Eric, to check if this strategy given by Luca was indeed true or was indeed optimal from a mathematical and AI point of view. And this is an example of a board game that I use for a teacher trainer, and there are a lot of interesting things to say on that and to work with. So I guess this is it. So if you have any question, just please ask.
Sign up first. Yeah, two questions. Like, is the focus exclusively on combinatorial games?
No,
No,
it's just it's because it's the example that I know well. So
okay.
the answer is no. We will like grasp a lot of different games.
Yeah, and the second question, was Lucas's strategy optimal?
Yes, it was.
Okay. Thank you. Thanks for the question.
The French game is also analyzed by Shu in because the Shu made in 1953 a game was it's called Ratio, with an accenter in it, and you have a lot of game boards then. And he analyzed in his book to the board game itself all the possibilities there. So, you know about that?
Yeah, you sent me.
I sent you. Yes, I sent you one.
And you sent me the rules of the different boards because they can be different.
Yes.
And Dennis worked on the translation because I couldn't read the, Dutch, but so we analyzed that as well because Shu gave variants of this game, and there are variants on the board as well. And so it changes the results. And
because he had made a blocking game. There's a blocking game, and there's also the game of the winning of one of the pieces.
Yeah.
Yes.
Yes.